Power functions are functions with one term in the form y equals a times x to the b, where a and b are real numbers. So power functions, here are some examples. Now take a look at those. Anything strike you? Maybe you're thinking, wait, that can't be a power function. That's not in that form. But we can rewrite this, can't we? Sure, we can remember that 6 times x to the negative 2 is just another way of writing 6 divided by x squared. So this is a power function. Same thing here. Wait, that doesn't look like that's in that form. But I could rewrite a radical. The cube root of x is really the same as x to the 1/3. So these are examples of power functions. Here are some examples of things that are not power functions. That has two terms. That has one term, but not in the form a times x to the b. Same thing with that. Now power functions are kind of fun. I just want to look at some 6 different kind of families. There are like 6 members of the power function family. And so let's just look briefly at those. One of them is y equals x to an even number. And for now, we're just assuming a, the coefficient, is 1. So I don't know, give me an even number. Sure, 2. So for example, y equals x squared. Well, we are all familiar with that. We know what that looks like, right? That's a nice parabola. If I had maybe another number like y equals x to the 4th, something like that, well, that's not a parabola anymore. It's going to be a little steeper, a little flatter at the bottom. But you'll notice that they look similar to each other. They have the same end behavior. How about y equals x to the odd? Like y equals x to the 3rd. Well, we know what this looks like too. That's like our classic cubic. And y equals x to the 5th, y equals x to the 7th will all have a shape similar to this. Will have the same kind of end behavior. It'll have the same kind of concavity, right? This is concave down and then concave up. Now sometimes students will say, well, wait, do I just have to memorize these? Like, how do I know a cubic looks like this? So I just want to remind you, and we've kind of forgotten this with all the years of poking things into calculators. Whenever you want to know what a function looks like, you can always plug in an x, get out a y. Plug in an x, get out a y. So I'm just going to pick some x values, some negative x values, 0, and some positive x values. And then plug in the x and get out my y. So negative 2 cubed is negative 2 times negative 2 times negative 2 is negative 8. Negative 1 cubed, negative 1 times negative 1 times negative 1, that's negative 1. 0 cubed, 0 times 0 is 0. 0. 1 times 1 times 1, 1. 2 times 2 times 2, 8. And I just lickety-splickety-quickety got 5 points. Negative 2, negative 8. Negative 1, negative 1. 0, 0, 1, 1, 2, 8. So for every single one of these functions that I'm going to show you, you don't have to memorize what they look like. You can actually just generate a table of points, plot the points, and look at them. Okay? So let's look at 2 more. If I had y equals x to the negative even, so here a nice example is x to the negative 2. Well, let's pretend we don't know what this looks like. Let's go ahead and make a table of values. Plug in an x, get out a y. Plug in an x, get out a y. I'll put in some negatives, a 0, some positives. Well, wait, negative exponents, that's really awkward. Let's rewrite that, shall we? X to the negative 2 is the same as 1 over x squared. Okay, so negative 2, 1 over negative 2 squared, that's going to give me a positive 1/4. Negative 1, that's going to be 1 over negative 1 squared. That's 1. 0, 1 divided by 0. Hold on. We can't divide by 0. That's impossible. That's undefined. So clearly, 0 is not going to be in my domain. Let's plug in a 1. 1 over 1 squared is 1. Plug in a 2. Okay, so right away I'm seeing some symmetry here. I can start to plot these points. Negative 2, 1/4, negative 1, 1. I know that's undefined. I'm going to have a vertical asymptote there. Okay, now these points aren't quite enough for us to know, but let's imagine putting a really, really big number, like 10. 1 over 10 squared. Wow, that's 1 over 100. That's practically 0. So I think this thing is going to get closer and closer and closer to 0, right? Oh, that's end behavior, isn't it? And so that's how we know it looks like that. Concave up, just to review concavity. As x is approaching negative infinity, my y is approaching 0. As x is approaching positive infinity, my y is approaching 0. And you can kind of see that in our chart. All right, let's do an odd negative, right? And again, let's rewrite it like this. Okay? We could do the same thing. I'm not going to do it right now, but I encourage you to pause the video and make yourself a little chart of values. And I think you'll find that you'll get something that looks like this and something that looks like this. Now wait a minute, that's different here. And that's because when I plugged in negative x values, when you multiply a negative times itself an odd number of times, you get a negative y, which is why I'm down here, right? There are two more that I just want to talk about in our families of power function. This is a fraction, like if I have x to the 1 over 2. Well, let's remind ourselves that really is the same as writing a square root. So we probably know square root functions look like this. But again, if you didn't remember that, make a table of values. Plug in an x, get out a y. Plug in an x, get out a y. And if you tried to plug in negative x's, you would have realized, oh, I cannot take the square root of a negative number. That's an imaginary number, not a real number. Similarly here, if I did y equals x to the 1/3, another way to rewrite that is a cube root of x. And if you plugged in some x's and y's, you'd realize, oh, that's going to look like this. I can plug in negative x's because a negative times a negative times a negative gives me a negative. So I just am picking some values here. You can pause the video and make sure I did that right. But if you plugged in a -8, you are going to get an answer. It's going to be -2. If you plug in a -1, right, the cube root of -1 is -1 and 0 and so on. So don't memorize what these look like. Actually, take the time, plug in some x's, get out some y's, and you will be able to know what they look like. So now let's just quickly review some of the vocabulary that we've been working with. So let's talk about the concavity of this. Concavity, we'll talk about this more when we get into calculus. It talks about how the slope is changing, right? So concave down is like an umbrella, right? So this is concave down for its whole domain. Here, this is concave down for x less than 0. And look here, ooh, that looks like a bowl, or concave up for x greater than 0. Let's look here, ooh, that's like a bowl or a satellite dish. That's concave up when x is less than 0. And ooh, that's like a Umbrella, that's down. Concave down for x greater than 0. So again, we're looking at the change in the slope. That looks like, ooh, an umbrella. So that's concave down for x less than 0 and concave up for x greater than 0. Okay? How about increasing and decreasing? A function is increasing when the slope is positive. So when you're looking for a function, if it's increasing or decreasing, your x's are just getting big, 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 and you're seeing what happens to the y. So here, my y is going up, and then it's coming down. So my function is increasing, and then it's decreasing. Here's my x is getting bigger. My y, it's just getting smaller. So this function is decreasing over its whole domain. Here's my x is getting bigger, going from the left to the right. What's happening to the y? Oh, it's increasing here. And what's happening? A little vertical asymptote. Oh, the y is still increasing. How about here? As the x is getting bigger, 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 my y is getting bigger, bigger, bigger. So the function is increasing over its whole domain. One last thing that we talked about is end behavior. End behavior is always a little tricky because you're moving either towards infinity or towards negative infinity. So you're asking yourself, what's happening to the y as you're leaving the page? So as I'm going to the right, as my x is getting bigger, 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 10, 100, 1,000, what's my y doing? Ooh, it's going way, 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 way down, getting really, really negative. So that is approaching negative infinity. What's happening here is x is getting really, really small, negative 10, negative 100, negative 1,000. What's happening to the y? It's going down, down, down. It's approaching negative infinity. Okay? Let's just do one more here, right? What's happening as x is approaching infinity? As x is approaching infinity, look at the y. Oh, it's getting closer and closer to 0. Right? Now, as I'm going to negative 10, negative 100, negative 1,000, as x is approaching negative infinity, my y is getting closer and closer to 0 as well. And remember I talked about making tables of points. You can look at your y values on those tables too to see if they're going up or going down. All right, my friends, this is a lot to keep track of, but the more you play with these power functions, the more comfortable you'll get with them. Have fun.